All right, hello everybody. Welcome back to Anti-Algorithm Math. We're here to prove the Riesz representation theorem, or at least get as far as we can. I try to keep these to an hour or so at the most. So we'll see how many steps we can get through. Just to recap where we are, this is a statement of the theorem from last time. And we did the construction. Okay, we'll have to refer back to this construction page probably a few times. We did some observations. We did step one, which proves subadditivity. This is essentially an outer measure condition. I mean, you can look into the finer points of what the outer measure condition is, but this is pretty much it. And then we had step two, which proves that compact sets are in MF. That's this sort of pseudo sigma algebra. It's not actually sigma algebra for reasons. But anyway, compact sets are in here. They have finite measure, right? And you can also calculate them as the infimum of values of the linear functional on um, functions that are greater than k, meaning that they're equal to 1 on k, and they satisfy the other conditions that I talked about before. Um, you know, I'm trying to be as complete as I can, but obviously, at a certain point, you got to leave stuff out because it'll be too much. It'll be too much on the screen at once, and no one wants to deal with that. Okay, so we proved step two. That's where we ended things. And I observed along the way, along with Rudin, that B, C, and E have been proven. We have constructed M and we have constructed the positive measure mu, but we have not yet proven that um, M is a sigma algebra. We haven't proven that mu is a positive measure. We haven't proven A, which is obviously the most exciting part. I mean, part A is like the reason why it's a great theorem. We also have not yet proven part D. Okay, so we're gonna do those at some point along the way here. Um, I'll let you know as we come to that, but that's just a little recap for you. So I just want to now pick up where we left off and head into step three. So let's do that. Step three. Okay, so step three is every open set satisfies, oops, not satisfies. So every open set, I'll call it V. So every open set satisfies basically the condition to be in MF. Okay, so it's going to be uh, let's go back here. It's going to be this condition here. Okay, that's what um, that's what I want to say for number three. Okay. Um, or yeah, that's what I want to say that it satisfies. So let me write that down. The measure of V is equal to the supremum. So basically we can calculate it by doing the measures of complex sets that are contained in V. Okay. So uh and this is just kind of an obvious observation. Hence V is in MF if the measure V is finite. Okay. So that's kind of a side comment. but let me just again remind you. So this is MF, right? So I'm saying that V satisfies this condition here, the third one. And so the observation is just that if the measure of V is actually finite, then we're in here, right? Because I mean, it's a subset. This isn't much of a condition here. This is just to remind you of what kind of thing we're talking about. It's not, I mean, it's not a shocker that an open subset is a subset. But if it also has finite measure, then because it satisfies this, it will be an MF. Okay, so that's all I'm saying here. All right. So let's do the proof. All right. Now Rudin does this in a particular way. I get why he wants to do it. If we think about what we're trying to prove, I mean, we know that the measure mu is monotone. So the measure of any compact set contained in V will be less than or equal to the measure of V for sure. Okay. So what we need to do is we need to prove that we can get as close as we want to the measure of V from below by a compact set. Okay. So if we let epsilon be greater than zero, then uh, by this is where we need to remember this other thing. So for V open, right, the measure of V is the supremum of the um, values of the linear functional on functions that are less than V, meaning their support is contained in V and they're between 0 and 1 and they have compact support and blah, 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 right? But it's the suprema of these. So we can get as close as we want to V from below, right, by these. Right? So basically we want to leverage these to get to a compact set, right? That's our plan. And if you remember that these functions here have compact support, you might get the idea of what our plan is going to be. Okay, so let's go back here. Um, by definition, there exists an f less than v such that the measure of v minus epsilon is less than lambda f. Okay. So lambda f will exceed this, right? There's an f that is less than v where lambda f is larger than this because these are approximating the measure of v by definition. Okay. So you can read Rudin's proof. He phrases this slightly differently, but I'm trying to do this in like classic analysis epsilon style. So like if we're approximating from above, he'll do plus epsilon, but when we approximate from below, he doesn't like minus epsilon. I don't exactly know why. It might just be a personal preference. Okay. Now, if W is open and contains the support of F, okay, so remember what that is. It's just the set of all x so that f of x is not equal to 0, but it's not exactly that. It's the closure of that, okay? Um, and this is compact by definition. Okay. So when I use this notation, I mean, this is Rudin's notation, but this notation here automatically implies that f is a continuous function with compact support. Okay. So let me just write that here. So f is in CCX. Okay. So it's a continuous function with compact support. Of course, we need that to be true to apply the linear functional. But in any case, I just want to remind you the support being compact is built into this notation here. Okay. All right. So now we have this, and I can go ahead and just call this set K, right? That's going to play the role of my compact set. Okay, so W now contains K. Okay. Um, so if that's true, then um, F is less than W, right? Because what does it take for f to be less than w? Well, it satisfies all the conditions that have nothing to do with w because it's already here, right? It's less than v. So it's one of those functions. It's a candidate. What's the extra condition we need for this? We need the support of f to be contained in w, and that's just what I assume. So I'm kind of just stating the definition here, but that's true. Okay. Uh, and so. Uh, if f is less than w, then that automatically tells me that lambda f is less than or equal to the measure of w, again by definition, right? So that's just going back to that, the construction of the measure, right? So W is an open set, so it's realized by supremums of these, meaning all of these are less than or equal to the measure of the open set, that they're less than, and so boom, we get this, okay? Thus, um, uh, thus, by step two. So by step two, we have that lambda of f is less than or equal to the measure of k. Okay. So okay. So what I proved is that if w contains the support of f, which is what k is, right? K is just another name for the support of f. Let me actually use a little color to highlight that point as well, okay? Just so we're remembering what means what here, okay? So that's the set K, okay? So by step two, we have this. So let's now remember, step two is here. So step two says that the measure of K is the infimum of these lambda Fs, okay? So okay, sorry, no. After reflection, I realized this is a mistake. Let me just fix this real quick. So it's not step two, it's actually like condition two of the definition. I mean, it's the construction. So so I'm just going to write definition here. So we're just going to go back to, again, the construction page. So the measure of any subset is given by the infimum of the measures of the open sets that contain that set. Okay, so the measure of K is equal to the infimum of the measures of the open sets that contain K. Okay, so what I've just proven here is that if W contains K, then lambda F is less than or equal to the measure of W. So if we take the infimum of all of these, we get the measure of K, and therefore the measure of K is greater than or equal to lambda F. Okay, sorry. It's I think when I was writing my notes, I got confused about the second thing here versus step two. It's clearly the second thing here that we want, not step two. Okay, sorry about that. All right, so by definition we have that. And I won't cut it. I won't cut it because I want you to see that mistakes are made, okay? It's actually important to understand, like if you want to learn how proofs like this are created, you need to understand the sort of trial and error that happens, either actual misunderstanding and actual mistakes, or just sort of superficial, like, oh, I'm referring to the wrong thing and what I said makes no sense, right? You need to learn to be comfortable with that. So I hope that by keeping that in, it'll show you that it's not only okay to do that, it is an essential part of the process. Okay? You have to get it out of your head that the point of stuff like this is to just produce a perfect proof off the top of your head with no sort of trial and error, no difficulty, no mistakes, right? That's not what this is about. Anyway, we have this, right? So now, uh, now we have, now we can put this together. So therefore, um, just by squeezing here, the measure of v minus epsilon, which is less than lambda f, which is less than or equal to the measure of k. This is less than or equal to the measure of k. Actually, it's strictly less. I mean, it doesn't really matter, but it is strictly less because I have a strict inequality here. Okay. And basically that's what I needed to find, right? I needed to find a K that's contained in V, which is implied by this condition. Okay. So I almost want to say that as well. Um, support of F is contained in V. Okay. So I know that this K here is contained in V because the support of F is just what K means here. K is just a shorthand for that, and that's contained in V, right? It's compact by definition, okay? And by the way we constructed this K here, we know that it's greater than the measure v minus epsilon, and that means that we can get as close as we want to the measure v from below by a compact set, and that completes the proof. Okay, cool. So that is step three. All right, let's roll on then with step four. All right, so step four is uh, if um, E1, E2, E3, and so on are pairwise disjoint. So that just means that if you take any two of these, the intersection is empty. Okay, so uh, for I not equal to J, EI intersect EJ will be empty. That's all that means. Okay, so if these are pairwise disjoint and all in MF, okay, then we have we have countable additivity. The sum, well, I'll write it the other way. I'll write it the way Rudin does. The measure of the union from I equals 1 to infinity of EI is equal to the sums of the measures from I equals 1 to infinity of the individual EIs. Okay, so that's the countable additivity. Um, if in addition, the measure of E, or the union is what I mean here. The union is finite, then the union of the EIs is also in MF. All right. So that basically just means that this union will satisfy that third condition, right? So let me just again take you back to that. So that says the union satisfies this. So basically what we're asserting there is that the union satisfies this. Okay, it can be approximated by compact sets from below. Okay, that's the point I'm making with that. Okay, so now let's get rolling on this one. Okay. Oh, and this one's a little long, so we'll see how it goes. All right, proof. So we first show that the measure of K1 union K2 equals the measure of K1 plus the measure of K2 for um, disjoint compact sets K1 and K2. Okay. We did something like this in a previous step, right? We're building up to this big union, but we're gonna kind of leverage our way up there, and we're gonna start with the simplest possible case, which is just two disjoint, not even two disjoint members of MF, but two compact sets. Now we did prove in a previous step that compact sets are all in MF. Okay, so these are special cases. So this is a special case of the thing we're trying to prove in general. Okay, let epsilon be greater than zero. Okay, classic analysis thing. Um, uh, so how do I want to say this? Yeah, yeah. So compact sets are closed in a Hausdorff space. Okay. Um, compact sets are closed in a Hausdorff space. Okay. And again, uh, with these topological preliminary facts, any of that, if I ever make an assertion or something that, strikes you as confusing, or who knows, maybe I'm even wrong, but whatever you want to say, if you want to make a request that I elaborate or correct my error or whatever, please leave it in the comments. Rate, review, and subscribe. We got our first subscriber. I'm super happy about that. All right, anyway. It's probably bad to put that in the middle of the video, but this is anti-algorithm math, right? So we're trying to succeed despite the way you're supposed to market yourself online. Anyway, compact sets are closed. So by Eurozone, there exists an F that is trapped between K1 and the complement of K2. Okay, so this is open because K2 is closed. Okay. So that means the support of F is in the complement of K2. Okay, so support of F is contained in the complement of K2. So therefore, f of x is equal to 0 for x in K2, and f of x is equal to 1 for x in K1. And that just comes from the first half of this here. Okay? So I just wanted to record. These are actually the conditions that Rudin wants, but I wanted to explain to you how you use Eurozone's lemma here specifically. Okay, now we actually will finally invoke step two here. So by step two, there exists a G such that K1 union K2 is less than G. And uh, lambda g is less than the measure of k1 union k2 plus epsilon. Okay. Um, so sorry, I don't like how that middle thing came out, so I'm just gonna sort of repair that a little bit. Okay. So let's go ahead and explain how this follows from step two. So if we go back to step two, it tells you that you can approximate the measure of a compact set from below by lambda f's that are where the f is greater than the compact set. So the only observations I need to make here are the union of two compact sets is compact. That's actually pretty easy because if you have an open cover of the union, you have an open cover of each one of the sets. So each one of them has a finite subcover. And if you take two finite subcovers and throw them together, you get a finite cover of the union. Okay, so the union is compact. So therefore we can approximate from above by a lambda g to any as close as we like. We can get as close as we like by lambda g's that satisfy this condition. Okay, so so now let's just remember a couple of things here. So we have f is a continuous function with compact support. And we have these two conditions. And then for G, we have this condition. Okay. So that means going to a new page here. So that means that we can note that K1 is less than F times G. Okay, so what does this essentially mean? So F times G is a continuous function with compact support. That's clear, I think. I mean, you can think through it, right? Where would it not equal zero? Well, both F and G would have to not equal zero. So it's contained in the intersection of the supports, you know, which is compact, right? Intersection of compact sets is compact in a Hausdorff space, at least. Okay, so it's a continuous function with compact support. It's between 0 and 1. What's the extra condition we need here? We need that it's equal to 1 on K1. So how do I know it's equal to 1 on K1? Well, G is equal to 1 on the union of K1 and K2, and F is equal to 1 on K1. Okay, so putting those two together, if we're in K1, G is equal to 1 and F is equal to 1 as well. And therefore, the product 1 times 1 is equal to 1. So this product, I'll put a little dot here so you understand. I mean, multiplication, not composition, right? I mean, it doesn't even make sense to compose these functions. But anyway, well, it might, but it probably doesn't. Okay. Anyway, so we have this. And we have K2 is less than 1 minus F times G. And that's for basically similar reasons, okay? Because, well, I'll let you think through this one because it's basically the same reason. You just have to go through what I just said. Okay. Uh, so uh, um, so that means that, first of all, mu of K1 plus mu of K2. So this comes from, let's see, hold on. Let me get my reference right here. Yeah, yeah, yeah. Uh, this comes from step two again. So it's less than or equal to lambda of F times G. plus lambda of 1 minus f times g. Um, I guess I'll put another set of parentheses there. Okay, so that just comes from step two. Okay, and um, now if I just combine these together using linearity, this is equal to lambda of f times g plus g minus f times g. So that's equal to lambda g. So we're just using linearity. Okay, because we have a linear functional lambda here, right? And the f times g's cancel out, so we get lambda g in the middle. Okay, and then let's now remember that lambda g um, satisfies this. Okay, so now this is um, less than mu of K1 union K2 plus epsilon. Okay, so now we see that therefore, if we let epsilon go to 0, we get that mu of K1 plus mu of K2 is less than or equal to mu of K1 union K2, and therefore they are equal by step one. Okay, so just remember step one. So helpful to have this. This was step one, the subadditivity. So we know, and this is for any subsets, by the way. So for two compact subsets, right, the measure of the union is less than or equal to the sum of the measures. So what we just proved here is the inequality goes the other way, therefore they have to be equal by step one. Okay, so that is now a proof of this. Okay, so I think in tradition, I know I'm not being super helpful here with my colors, but just to follow the trajectory, that means we've proven this for disjoint compact sets now. Okay, so we now have that available to use as we like. Okay, so now let's continue. Um, if um, if the measure of the union from I equals 1 to infinity of the EIs is equal to infinity, okay, then, okay, hold on. Let me make sure I'm reading this right. Yeah, so if the measure of this union is actually equal to infinity, then again, going back to step one, we have subadditivity. So if the thing on the left is infinity, then the thing on the right's infinity too. So they're equal, as in infinity equals infinity. Okay. So then result holds by step one. Okay. So so that's the first thing we needed to get out of the way. If the measure of the union's infinity, no problem. Okay, we could have said that before. We could have said that back in step one, right? That wasn't useful until now. Okay, so now we can assume without loss of generality. So I think the way I'm using without loss of generality is slightly incorrect here. Normally you do it when you say you're going to prove a special case, but like by a symmetry property or something, it kind of implies all of the cases. That's not exactly the way I'm using it here because I've already argued why it's without loss of generality. So it's not like you need to be reminded. So anyway, it's bothering me that I'm saying this, and yet somehow I feel it's true. I've explained why we can make this assumption, but we are nonetheless making a restrictive assumption. So I just want to make sure you understand that we're not losing generality in the final result here. Okay, so I'll put it in parentheses as a compromise. So we're going to assume that the measure of this big union is actually finite. Okay? Which, according to the result we're trying to prove, means that the measure of the infinite sum is also supposed to be finite. Okay? Um, and again, we need an epsilon. Okay? Now, I'm just gonna, I'm just gonna let epsilon be greater than zero from before. Even though we let it like go to zero here, I'm just gonna avoid saying let epsilon be greater than zero again. I hope you'll forgive me for doing that. It's technically a different epsilon from the one I used here. It's just a tool, right? This is why we need non-standard analysis. We need like infinitesimals, right? So I can just like throw an infinitesimal in there and call it a day. Anyway, sorry. Um, since the EIs are in MF, so we already know they all have finite measure, for example. So just to reorient you and myself, our assumption is that these are all in MF, right? Okay. So since we have that, there are compact sets HI um, uh, contained in EI, okay, for all I, um, such that the measure of HI, the compact set, is greater than, oh, he does a minus here. Oh, Rudin. Oh, Rudin. Okay, so we're not going to do minus epsilon here, right? Again, remember this trick happened, I guess it was in step one, right? Step one is when we did a trick like this. Right? Yeah, step one has a very similar argument. So we don't want to put epsilon here because we're going to add these up. Okay, so what we're going to put instead is epsilon over 2 to the power I. Okay? It's just a friendly thing. And, pretty much any series that converges, like you could put here and the argument goes through just fine. It's just 1 over 2 to the I converges to 1, and that's pretty nice. Okay. Um, so now we have this. Oh, do we remember what the condition to be in MF is? Let me just remind you about that. So we're using this condition here, right? You can approximate it from below by compact sets, right? That's the condition you need to be in MF. And so we can do that, right? We can approximate it from below. And so the HIs here are those compact sets. Okay. So now let Kn equal the union from I equals 1 to n of Hi. So uh, these are compact as well. All right. Again, because it's a finite union of compact sets, I basically outlined the argument why a finite union of compact sets has to be compact. That's pretty easy. Um, so now, but by induction on the two subset case, so remember that we proved this for two compact subsets. Now, if you apply induction, so yeah, this is this is actually very similar to step one. I almost wish I gave this to you as an exercise after you have step one, because we're just kind of redoing things. So we have this, right, which means we can actually do this for a finite collection of any finite collection of compact sets that are disjoint. Okay? So by induction, uh, on uh, by induction on the two subset case, um, which incidentally, uh, wait, hold on a second. Hold on a second. Okay, good. It was no problem at all. So just remember, got to keep this all straight. The EIs are pairwise disjoint, and the HIs are subsets of the EIs. So the HIs are pairwise disjoint also, right? If they're sitting inside pairwise disjoint sets, they have to be pairwise disjoint as well. Okay? So so again, we have this by induction for any finite collection of compact sets. Okay. And so by induction on the two subset case, we get that first of all, um, uh, the measure of this is the big union here. Sorry, I meant to put infinity at the top because I really want it to be the big union. Infinity. Okay. Is greater than or equal to. So this is just by the monotonicity. So greater than or equal to the measure of the Kn, which is what I just wrote down here. It's the union of the first n HIs, and that's equal to the sum of the I equals 1 to n measure of the HIs. So the induction on the two subset cases giving you that equality right there. Okay? Just to clarify. And then similarly to what happened in step one, because we have this, if we add up the measures of the HIs, then we're going to get the sum of the EIs from I equals 1 to n minus epsilon. Okay? So that's going to be greater than the sum from I equals 1 to n of the measures of the EIs minus epsilon. And just to clarify, that epsilon is not part of the sum. Okay. We did the sum already. It's sort of part of the story inherently. Okay. Um, so so now let epsilon go to 0. Okay, so this goes away, and we get that this is greater than or equal to the sum from I equals 1 to n, but that holds for any n. Then let n approach infinity, and we get that the measure of the union from I equals 1 to infinity of EI is greater than or equal to the sum from I equals 1 to infinity of the measures of the individual EIs. Okay. You do have to be a little careful about your epsilons and your n's here, so, think it through as you like. Um, but we get this, and so we have equality by step one. Okay, so remember, step one is the subadditivity, the inequality going the other way for any subsets, and no assumption at all. We're getting the other way here, and that means that we have equality by step one. And these are finite values, so we're getting a real strong, true equality here. Okay. So that proves the main point here, which is this. Okay, but now we're going to also prove that the union of the EIs is in MF, which basically means that we can approximate it from below by a compact set that's contained in the um, union here. So uh, Okay, so just trying to get this straight here. Okay, yeah. Okay, yes. Now, we're already assuming that the measure of the union from I equals 1 to infinity of the EIs is finite, right? So we're already assuming that. I want to prove that it's in MF. So notice that um, the measure of the union of I equals 1 to infinity of the EIs um, okay, hold on. All right, give me 1 second. I'll be right back. All right, sorry about that. I'm just thinking about how I want to phrase this, and I didn't really come up with anything. So we have this now, okay? And so for epsilon greater than 0, we um, can pick an n such that the measure of the union of the EIs um, is is less than, I think I want to say less than here. Yeah, less than the sum from I equals 1 to n of the measure of the EIs plus epsilon. Okay. Okay, so we know that this sum converges to this, right? And you know, and it's a finite sum and so on. Okay. So that means that uh uh that means that the if we go out far enough in the infinite sum, we'll get as close as we want to the limit value, which is this. Okay, so we can get within epsilon, right? We can get within epsilon of the limit value, and we know this is approaching from below, so like this inequality direction makes sense. And another way to put it would be this is greater than this minus epsilon. Okay, so we pick that in. And then we go back to our, example. We go back to our construction from here. We can still pick these compact sets that do this job, and we can still have this inequality here. Okay, so that means that this sum here, okay, um, is less than k capital N plus epsilon. Okay. Um, so this is less than or equal to the measure of k n plus epsilon um, by above. Okay. And kn here is compact. Let me use a different color for that. So Kn is compact, capital N, right? And and you know, this is equal to the measure of K capital N plus epsilon. Okay. So flipping this whole thing around, um, that means like here, let me clarify to you what I'm talking about. So, you know, this is less than or equal to this. Okay. So that means that to phrase it another way, so um, the measure of the big union minus epsilon is less than or equal to the measure of Kn, which is compact. So that means we can approximate from below, right? So that's a condition I'm trying to prove, right? I can find a subset of that big union that approximates the measure of the union from below as close as I want. And here I got within two. Oh, I forgot my two. Okay. Here, I got within two epsilon. Okay. Which means I can get as close as I want, right? Two times epsilon is as good as epsilon. That's where like infinitesimals are cool, because if you're doing infinitesimals, like the distinction between epsilon and two epsilon is basically none. So you don't have to worry so much about that. But anyway, therefore the union I equals one to infinity of the EIs is in MF. And that concludes step four, the proof of step four. Okay, cool. So yeah, so that's the end of step four. Um, is it time to stop, or should I push for step five just to see if I can get us through here? Um, let's see. Um, yeah. Yeah, step five is kind of a technical thing, and it's pretty short. So let's just go ahead and do it because it's not an exciting way to start anything. So let's do step five, and then we'll call it there. So step five says that if E is in MF and epsilon's greater than zero, then there exists a compact K and an open V such that K is uh, contained in E, which is contained in V. So we're just trapping our set E between a compact and an open set. You should already be thinking Eurozone when I write this down, right? Eurozone is looming as soon as I have a condition like this. And notice I'm specifically trapping a certain kind of measurable set here, right? I'm specifically trapping these. It doesn't actually have to be measurable, but um, I'm trapping a certain kind of subset between a compact and an open. And compacts and opens are the friendlier ones because we can use those to get functions, which we can then use the linear functional, right, to connect back to like what we're actually trying to do, right? So that's sort of the game of this whole proof. Anyway, what I've said so far isn't very exciting. And the more important thing here is that K and V are sort of as close together as they can be. All right. So basically, I want to make them as close to E as I can, and I'm measuring closeness by measure here. I'm using the measure to measure. Wow, look at that. So that means the measure of V minus K will be less than epsilon. Okay, so that's what I can do. Okay, so we know by definitions there exists K contained in E and um, a V. Um, uh, there exists a K and there exists a V. I wrote it on the other side, but anyway, such that the measure of uh, V is less than the measure of E plus epsilon over 2. And so that's approximating the measure of E from above by an open set. We know we can always do that. Okay. So this is always true for every subset. Okay. So there's nothing magic here. But because E is in MF, remember MF means I can approximate with compact sets. Okay. Not exactly sure why it's called F. I almost think MC or MK or something would help me remember better. Why is it called MF? I don't know. Anyway, since it's in MF, I can also have, um, or I can also approximate from below by a compact set. So the measure of E minus epsilon over 2 is less than the measure of K. Okay. Um, so since uh, K is closed, V minus K is open. Okay. So V minus K is in MF. Okay. So that's by step 3. All right. So just remember what we proved in step 3. Step 3 was this. Okay. Step 3 was this. Okay. We already know that the measure of V has to be finite. The measure of V has to be finite because of this condition here. Okay. So this is an open set. And the measure of this is finite because the measure of V is finite. Okay. So it's open and it's in MF. Therefore, by step 3. Okay. So far, so good. So by step 4, the one we just did, um, the measure of K plus the measure of V minus K. So observe, first of all, compact sets are in MF. See, we have to verify all of this constantly. So I think that was step 2. Yeah. So in step 2, we get that compact sets are in MF. Okay. Step 3 says that open sets are in MF if they have finite measure. Okay. So that now means that K and V minus K are both in MF. And therefore, so is their union. But of course, their union is just equal to V here. Okay. And the fact that we can sum together these sets is what comes from step 4 here, this one, right? So we're just using this because all the relevant sets are in MF. So that means we get additivity through the measure. Okay. And so now we know that the measure of V. The measure of V is less than this. Okay, yeah, let me use a little highlighter here. So measure of V is less than this. Okay. Um, plus epsilon over 2. Okay. And so if I move the epsilon over 2 to here, right, I get that this is less than the measure of K plus epsilon over 2. So I get epsilon over 2 plus epsilon over 2. Okay. So that then tells us that this is less than um, the measure of K plus epsilon. Just putting together uh, uh, the above inequalities, and now we can just subtract the measure of K from both sides, and we get that the measure of V minus K is less than epsilon. And that's what we wanted to prove. Just a little technical result there. Okay, so I'm happy with that. So I think that's going to be a place to stop. So I'll be back in the next one with the next steps, however many I can get through. I would love to get through this. I would love to get through this in, fewer videos, but if I actually care about the details and I want to explain what's happening, I feel like I need to take my time with this stuff. So anyway, thanks for joining me. Please rate, review, and subscribe. Keep the channel going. Give me a comment. Let me know what you would like me to do in the future, or let me know what you want me to comment more on, or like correct my mistakes, whatever you want to say. Engagement is cool. I'm really excited about the idea of doing some real stuff on YouTube, not just, calculating some silly integral or whatever, right? This is like deep and super interesting math, and I hope you're enjoying it as much as I am. All right. Well, with that said, I will say thank you for watching, and I'll see you next time. All right. Bye, everybody.